Okay, let's take a look at Achieve section 4.4, number 13. Here we're dealing this function here, and there's three basic questions. Find the critical points that correspond to local minimums, and then find the critical points corresponding to local maximums. So kind of two questions there, actually. Find the values at which points of inflection occur for this function, and then determine the intervals where the function's concave up, and then the intervals where it's concave down. Okay. First note that the domain of this function is all real numbers, because for any value of x, you'll never be dividing by 0, because the denominator, notice x squared plus 30, is always at least 30 or more. So it's always a positive value. So you're never going to be dividing by 0. Domain is all real numbers. That's important here. Okay, so find the critical points. We're going to need to find the derivative. And so I'm going to use the quotient rule. So the derivative of the top, x, which is 1, times the bottom minus the top times the derivative of the bottom, which derivative of the bottom would be 2x over the bottom squared. Simplifying this out gives me x squared plus 30 minus x times 2x is minus 2x squared. And so I've got 30, and then x minus 2x squared is negative x squared. Okay, so there's my derivative. Now the denominator is never 0, as we've already talked about before. It's always a positive number, greater than or equal to, in this case now, 30 squared. But the top, when is the top going to be 0? Because then the derivative will be 0. So the derivative is 0 when that numerator is 0, which is true when x squared is 30, or taking the square root, x is either plus or minus the square root of 30. 30 has no perfect square factors, and so this is as simplified as we can write that. So you need to show the derivative, and then to determine which critical points, so these are the critical points here, but they want to know which one corresponds to local min, which one corresponds to local max. So you have to show a sign check on the test for this. Again, you can do that in a table like they do in some of the book problems. I like to just draw a real number line. Here's negative root 30, positive root 30. I know the sign, the derivative is, of course, 0 at those 2 points. And then I just check these intervals in between. So if I pick a number between like 0, if I plug 0 in, of course, the bottom is going to be positive number. 30 minus 0 squared is 30. Positive divided by positive is going to give me a positive. If I pick values greater than the square root of 30, for instance, pick 100. I plug in 100, 30 minus 100 squared is a negative number. The denominator is positive, and so a negative divided by positive is negative. Similarly, over here, we get negative. So we can tell by the first derivative test, since our derivative changes from negative to positive, that we have this critical point corresponds to a local min. We have a local minimum at x equal negative square root of 30. At positive square root of 30, we have a sign change in the first derivative from positive to negative, meaning what changing the function itself is changing from what increasing to decreasing. Therefore, we have a local max at the square root of 30. Okay, so that's the first part. The second two parts, we need the second derivative for, so I need to take the derivative of the derivative. Again, I'm going to use the quotient rule. So I've got this up here. I take the derivative of the top. What's the derivative of 30 minus 2x? So the answer is negative 2x down here, times the bottom, which is x squared plus 30 squared, minus the top, 30 minus x squared. Notice I have that in parentheses, times the derivative of the bottom. Now the derivative of the bottom is by the chain rule, because the outer function is u squared, the inner function is x squared plus 30. So I bring the 2 down, I get 2u to the first power times the derivative of the inner function. What's the derivative of x squared plus 30 again? It is 2x. So this is by the chain rule. Let's clean this up a little bit. Okay, or don't forget, over the bottom function, which was x squared plus 30 squared. Okay, so simplifying the bottom, of course, squaring squared gives me multiply to the 4th power down here. And then here, I'm going to do 2 times 2x is 4x, bring that out in front. And then x squared plus 30 is this part, and 30 minus x squared is that part. Okay, so far so good. What I'd like to do is simplify this by factoring the numerator. Notice I have a common factor of -2 I can pull out, common factor of x, and a common factor of x squared plus 30. I've got 2 of them here and 1 of them here, so I'll pull out the smaller power. So I'm going to do that. I'm going to factor out the negative 2x, x squared plus 30. I'm going to factor that out. What's that going to leave from this first term? Well, I've got 2x squared plus 30, so it's going to leave me 1. Here, if I factor negative 2 out of 4, that leaves me positive 2. Notice negative 2 times positive 2 would give me the negative 4. I pulled the x out, and I pulled the x squared plus 30 out, so I'm just left with the 30 minus x squared. Okay. Now, in the brackets, this stuff can be simplified, right? Because I've got 30 plus what? 2 times 30, this 60. 30 plus 60 is 90. And I've got x squared plus 2 times negative x squared is negative 2x squared. X squared minus 2x squared is negative x squared. So this all simplifies down to 90 minus x squared. Notice I can simplify further. This x squared plus 30 can cancel with one of these, x squared plus 30. So we're left with 3 down here, and that's gone. So I just have the negative 2x, 90 minus x squared over x squared plus 30 now to the third power. So there's my simplified second derivative. Notice the denominator again is always positive because x squared plus 30 is always 30 or more. And then, of course, cubing it, but it's still a positive number. So it's going to be 0, though, when the numerator is 0. And so when this is 0, that's going to, I've got it factored already. Either the 2x is 0, which means x is 0, or 90 minus x squared has to be 0, which means x squared is 90, which means x is either positive or negative the square root of 90. But square root of 90 can be simplified because there's a perfect square factor of 9. So I can do square root of 9 times square root of 10 is the square root of 90, but the square root of 9 is just 3. So there's how we would simplify the square root of 90. And so I've got 0 plus or minus 3 square root of 10, where the derivative, second derivative is 0. I do a number line of that because I do need to see that there's indeed a sign change for there to be points of inflection. And just checking again, I'll let you compare notes, but plugging in values of x on each of these intervals into the second derivative, which is this right here, right before I simplify it, gives me this sign convention. Okay. So if you have questions about that, let me know, but that's how you what the signs are. And so we can tell because there are sign changes in the second derivative at each of these values, then inflection points occur at all of those values. Oops, I forgot to include 0. Okay, 0. I think in Achieve you have to list each one, so you can't do this plus or minus, but at any rate you have to list each one. So you list minus 3 square root of 10, 0, and 3 comma 3 square root of 10. Let's just do it that way. So negative, put a negative there, and then 3 square root of 10. Those would be the 3 locations for any points of inflection. Notice we have to have a sign. Can you have a situation where the sign does not change? Yes, you can. It could be plus here and plus here, which means that would not be a point of inflection, right? Would not have a point of inflection occurring at that value. So don't just assume because the second derivative is 0 at these points, don't just assume that it's going to have an inflection point at that location. Show the sign check. Also, the sign check gives us the intervals where we're concave up, where the second derivative is positive. So from negative 3 square root of 10 to 0. And then also positive from 3 square root of 10 to infinity. And then we're concave down where the second derivative is negative on these two intervals here and here. And so that's how this problem is done. A little bit involved in the simplification of that second derivative, but I hope that makes sense. And again, as always, if you have any questions, please let me know.